So as I was saying, the acetate ion has a conjugate acid with a pK of 5.8, and this ethoxide, which is considered a stronger base, has a conjugate acid with a pK of 16. So from the conjugate acids, the acetic acid is a stronger acid and has a weaker base than the ethoxide, which has a weaker acid and a stronger base. Another way to immediately look at these bases and see that one of the two is weaker and one of the two is stronger is the difference between localized and delocalized electrons. Localized electrons will be present on a stronger base, and delocalized electrons on a weaker base of equal charge. So they both have, both molecules, both bases, the acetate ion and the ethoxide, have a charge of -1, and the ethoxide has localized negative charge, whereas the acetate has a delocalized negative charge. A localized negative charge is always going to be a stronger base than a delocalized negative charge. Okay? So when a secondary alkyl halide reacts with a weaker base, it's going to favor a substitution product. And you can see that this particular SN2 with a weak base favors 100% substitution. I would not tell you to assume that that is always going to be the case, because it won't. And in a secondary alkyl halide treated with a strong base is going to favor an elimination product, but it will still produce the substitution product to a minor amount. So here we have the secondary alkyl chloride 2-chloropropane reacting with an ethoxide ion, which is in the class of alkoxide bases. And an alkoxide base is basically a deprotonated alcohol. So any substance to which, when you add one proton, it becomes an alcohol group is an alkoxide ion. So the ethoxide ion, being a stronger base, when it reacts with 2-chloropropane, produces in majority the elimination product, 1-propene, and in minority the substitution product, let me think of the name. Let's see. Ethoxy 2-propane. Ethoxy 2-propane. Or 2-ethoxypropane. 2-ethoxypropane. Yes, that would be the name of the substitution product. And the elimination product is 1-propene. Okay, and for secondary alkyl halides, bulky bases are going to favor elimination. So here we have our 2-chloropropane reacting with the bulky base, DBN. Or wait, is it DBN or DB? Yes, this is DBN. Also one called 1,5-diazobicyclo-430 non-5-ene, which is much easier just to say DBN. And DBN is going to react with the secondary alkyl halide to produce the E2 elimination product. So a bulky base with an secondary alkyl halide is going to favor elimination. All right, so in addition, not only speaking about secondary alkyl halides, but about alkyl halides in general, a high temperature for an alkyl halide with a strong base is going to favor elimination. So at just above room temperature, 45 degrees Celsius, the 2-bromopropane reacts with hydroxide ion to produce approximately a 50-50 mixture of substitution, SN2, and elimination, E2. If we increase the temperature to 100 degrees Celsius, we have a clear favorite of E2 elimination at 71%. So raising the temperature by about 55 degrees Celsius increased the yield of the elimination product by 22%. And that is because elimination has greater entropy of transition state. So greater change in entropy at transition state. And that's what that little double cross means, if you remember. S is entropy, delta is change, and this cross is transition state. Different color. The cross is a transition state, okay? And so elimination forms 3 products and substitution will form 2 products. Elimination forms 3 products and substitution forms 2 products. Sure. Okay. SN2 and E2 conditions for tertiary alkyl halides. The only possibility is E2 elimination. Tertiary alkyl halides cannot undergo SN2 substitution. So a tertiary alkyl halide where 100 will undergo only E2 elimination as the only product with a tertiary alkyl halide. Okay, but what about tertiary alkyl halides under SN1 and E1 conditions? Well, under SN1 and E1 conditions, we're going to obtain both the SN1 substitution product and the E1 elimination product if we have a tertiary alkyl halide. First of all, what are SN1E1 versus SN2E2? Well, SN1E1 is usually indicated by a neutral uncharged base, where SN2E2 is usually indicated by a nucleophile or base that has a formal charge. Okay, so looking at SN1E1 conditions for a tertiary alkyl halide. In a weak base, such as water or methanol, substitution is going to be favored for a tertiary alkyl halide. E2 elimination of a tertiary alkyl halide is only going to be favored if we have a strong, as I said, formally charged base. Now, in the lecture notes here and in your in the in-text chapter notes, we are referring to the alkoxide ions as these negatively charged oxide ions. But when you see these bases in your homework or on an exam or on the ACS test, they are never written in this form because that's not how they would be sold. They would be sold for the sake of stability in solution with sodium ions. And so when you see this written on a test, the way that it will be expressed is as a salt with sodium. So it will say NaOCH2CH3, and you have to make the connection that sodium, oxygen, CH2CH3, sodium is simply the counter ion, which is a spectator, and that the OCH2CH3 is the anion that is the base or the nucleophile. Okay? And so this base will be expressed in this way in the homework and on the exam. Now, it's formally charged, and that makes it E2 conditions. And E2 conditions with the tertiary alkyl halide will give us only E2 elimination. The weaker base, which has no formal charge, favors SN1E1 conditions, and it will primarily give the substitution product. Notice that it is 81% substitution and only 19% elimination under conditions where we have a weak base. So, summary of the products obtained from substitution and elimination reactions. Primarily, for a primary alkyl halide, SN2 and E2 will have primarily substitution, unless there is steric hindrance in the alkyl halide or nucleophile, in which case elimination will be favored. But primary carbons cannot undergo SN1E1 solvolysis reactions. For secondary alkyl halides, both substitution and elimination occur. The stronger and bigger the base and higher temperature, the greater the percentage of elimination. So things that increase the elimination product for the secondary alkyl halide are stronger base, bulkier base, and higher temperature. If you have a weaker base, a smaller base, and a lower temperature, then you may have favored substitution. Now, in general, they're going to say that secondary alkyl halides cannot undergo SN1E1 solvolysis reactions, but in practice, that is not correct, and the ACS test will not consider that correct. Secondary alkyl halides can undergo SN1 and E1 reactions if we have a neutral base. However, it is not as common or high yield. It's a very low yielding reaction. Finally, tertiary alkyl halides will undergo only E2 elimination, but in SN1E1 conditions with a neutral base, we will undergo both substitution and elimination, but substitution will be favored. Okay, so we're going to call certain substituents on a chain special names. Okay, so a CH2 benzene ring group is a benzyl group, and a benzene ring group is simply a phenyl group. So when would this come into play? Okay, say we have a 7-carbon alkene with a group at carbon that is a benzene ring. Now, if you remember, the longest chain containing the double bond is the major group, the suffix. So we have a 7-carbon chain containing a double bond and a 6-carbon ring. The 7-carbon chain is going to win. So this is a 1-heptene, and then the phenyl group would be a prefix substituent. So it would be 4-phenyl, and that should be a N, but it looks like an H. So I'll fix that. And 4-phenyl, 1-heptene. Okay. Now, same thing, but with a benzyl group, what you would have is your 7-carbon chain. How about an 8-carbon chain this time? And at carbon 4, a benzene ring, but an elbow before the benzene ring starts. So now what we have is 4-benzyl, 1-octene, because I drew 8 carbons for this main chain. Okay, so that's how those terms are going to be used. But more importantly, they are also going to refer to the first CH2 group off of the ring as the benzyl carbon. Okay, that's the benzyl position or the benzylic position. Okay. Benzylic carbons are like allylic carbons. They are the carbons next to a sp2 hybridized carbon in a pi bond. And the benzylic carbon cannot undergo elimination reactions if there is not a beta carbon that is sp3 hybridized. And so a benzylic carbon and allylic carbons, which do not have beta carbons that are sp3 hybridized, will selectively undergo SN2 substitution, and there will be no elimination because there is no beta carbon from which to eliminate a hydrogen. We cannot eliminate a beta carbon, a beta hydrogen. We cannot eliminate a hydrogen from a beta group that is sp2 hybridized. Okay, so I have a note. The beta carbon has a double bond. No elimination allowed. And we keep the red consistent color. No elimination allowed. If the only beta carbon is an sp2 pi bonded carbon, then elimination is not allowed, and the only option is the SN2 substitution product. Okay? What about SN1? Well, yes, SN1 is possible. We do create stable carbocations. And so the difference between when it goes through the SN2 mechanism and the SN1 mechanism is the base. Strong negatively charged, formal negative charge base, SN2 reaction. Neutral uncharged base, SN1 reaction. Okay, so if we have a neutral uncharged weak base, we'll go through a carbocation first, and then after the cation forms, the nucleophile, in the top case, the alcohol, in the bottom case, the water, will bond to the positively charged carbon to produce the substitution product. So an SN1 reaction of an allylic halide, you have to realize, can form two products because of rearrangement of the carbocation. So in the case where the double bond is between carbons, we will get one product with substitution at carbon 1, giving the more substituted double bond. This is disubstituted alkene. But the cation with a positive charge at carbon 1, where the bromine leaves, can rearrange with the bonding pi electrons moving to make a double bond at the sigma bond between the CH and the positively charged CH2, which moves the charge from carbon 1 to carbon 3. So once carbon 3 has the charge, then the nucleophile, water, can bond at carbon 3. Benzylic and allylic halides can only undergo E2 reactions if they have an sp3 hybridized beta carbon. So notice here I've highlighted in yellow the two beta carbons. We have sp2 beta carbon on the ring and sp2 beta carbon at the pi bond, but we do have sp3 beta carbons on the other side. Now that we have sp3 beta carbons, elimination is favored when we have a strong base. And so with these formally charged bases, that favors E2, formally charged negative base favors an E2 elimination, so that the methoxide will remove a proton from this beta carbon, the sigma bonding electrons will generate the double bond, and the bromide will get kicked off. We can draw this in short without drawing the whole molecule. So just pretend that on the other side of the squiggly line is the rest of the molecule. And what we get is the ethoxide. Oh, I should draw marker 8. Oh, no, it shouldn't be on that side. Okay. Da, 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 da. Anti-elimination. Okay. So our strong base will come in, remove the proton, the sigma electrons generate the pi bond, and the bromide is kicked off. We get our E2 elimination product, which creates a conjugated diene. If we have an allylic alkyl halide, and delocalization energy is always favorable, so elimination is the favored product because it results in delocalized electron density. For the benzylic carbon, we have, again, one sp2 beta carbon and one sp3 beta carbon. The ethoxide will come and remove one of the hydrogens. The bonding pair of electrons will go to make a pi bond between the alkyl the halide carbon and the carbon that lost its proton, and the chlorine gets kicked off. that gives us our allylic tri-substituted double bond. So this is a very stable product and favored over substitution, which would not result in delocalized substitution. The SN2 product with these reagents would not result in delocalized electron density, therefore it is not favored. So the elimination is favored because it results in delocalized electron density through conjugated double bonds. We also, benzylic and allylic halides undergo E1 reactions. What's the difference between the E1 and the E2? Again, the E2 involves strong, formally negatively charged base, where the E1 involves a neutral base. So what occurs is that we do have a beta carbon with protons that is sp3 hybridized. We will go into the carbocation, the base will remove a proton, and we will get a conjugated pi bond. And because it is delocalized electron density, it's favored over the substitution product where the alcohol oxygen bonds at the positive charge. So if we compare substitution and elimination products, you see that the substitution product does not have any delocalized electrons except for in the benzene ring. And the elimination product has both the benzene ring and one additional pi bond that is delocalized. And so the elimination product is favored. The E1 is similar. It produces an allylic cation by elimination of a first kicking off the bromine to form the cation, and then the base removing a proton from the beta carbon to give a pi bond that is conjugated to the already existing pi bond. And then knowing that resonance will allow this pi bond to shift to between these two carbons, we get a secondary cation, or we get a second cation. But I want you to notice that these two cations drawn by resonance are identical. 1, 2, 3, 4, 5. So this is with a cationic charge at carbon 4, and the other cation is also a cationic charge at carbon 4 and a pi bond between carbon 2 and 3. They are identical, just flipped over, okay? And so they produce only one product, which is 1,3-pentadiene. So you have to go through the work to determine if your allylic alkyl halide is going to result in two different products or one product, and it will only result in one product if the two carbocations possible through resonance are identical. Okay, this is a good place to stop.